Welcome back to Networking Explained, episode 11. And today we're tackling a piece of tech that powers almost every video call you've ever made. It's called WebRTC, and the magic is right there in the tagline. Browser to browser, directly. No server sitting in the middle relaying your video. Just two peers talking straight to each other. Let's unpack how that actually works. So before we get to the solution, let's understand why it matters. In the traditional setup, every single video frame has to travel up to a server, then back down to the other person. And that round trip costs you twice, once in latency and once in some pretty staggering bandwidth bills for whoever runs that server. Which raises the obvious question, what if two browsers could just send audio and video straight to each other, cutting the server out entirely? That's exactly what WebRTC was built to do. So here's the definition in one breath. WebRTC lets browsers and apps exchange audio, video, and data directly with each other, peer-to-peer, in real time. And there are three things worth holding on to. The media flows directly between peers. It's baked right into the browser with no plugins or extra installs, and every stream is encrypted by default. Security isn't an add-on, it's the baseline. To make that concrete, here's the analogy I like. Imagine a mutual friend introduces you to someone, they swap your phone numbers, you both dial in, and from that point on, the two of you talk directly. The friend isn't listening, isn't relaying messages. They've stepped away. WebRTC works exactly like that. A signaling server handles the introduction. The peers exchange what's called SDP and ICE information, and once the connection is up, the server is completely out of the media path. Now let's look at that same idea as a diagram. In step 1, both peers reach out to the signaling server to swap their SDP and ICE details, essentially their network coordinates and media capabilities. Then in step 2, they open a direct encrypted channel between themselves and the audio and video flow straight across that link. The server's job is done the moment the introduction succeeds. Let's zoom in on that introduction step. The SDP offer and answer is where each peer says, here are the codecs I support, here's the media I want to send, here are my parameters. Basically a compatibility handshake. ICE candidates are the list of possible network paths the other side can try to reach you on. And the channel that carries all of this. That's on you. WebRTC deliberately doesn't pick one. So a WebSocket or even a REST endpoint works fine. Once the signaling is out of the way, the peers still face a real problem. Most devices sit behind a NAT or firewall, so they don't actually know their own public address. That's where stun comes in. A tiny server that essentially says, here's how the internet sees you, so the two peers can wire up a direct connection. But sometimes the firewall is just too strict, and direct simply won't happen. That's when Turn steps in and relays the media through a server. You lose the pure peer-to-peer benefit and pay for the bandwidth, but the call always goes through. With the connection problem solved, let's look at the actual APIs you'll touch in code. Get User Media is your gateway to the camera and microphone. It's what pops up that permission prompt in the browser. RTC Peer Connection is the heart of it all, the object managing that direct peer-to-peer link for audio and video. And then there's RTC Data Channel, which is the unsung hero. It lets you send arbitrary data between peers, which is why WebRTC quietly powers things like multiplayer games and browser-based file transfer. And that data channel hero moment is a perfect bridge into where WebRTC actually shows up in the wild. The obvious ones are video and voice calls, plus screen sharing, think Google Meet or Discord. But it goes further. Live multiplayer games use it for low latency state sync, peer-to-peer file transfer skips the server entirely, customer support widgets embed it for instant face-to-face help, and IoT devices stream camera feeds directly to your browser. One protocol, a surprisingly wide footprint. So what does this actually look like when you sit down to write it? Surprisingly compact. First, Get User Media asks the browser for camera and mic access and hands you back a media stream. Then you spin up an RTC peer connection and attach each track to it. The third step, signaling, where the offer and answer get exchanged, is the part we'll unpack next, because that's where the real choreography happens. Before we dive into signaling, it's worth pausing on a question that comes up constantly. How does WebRTC actually differ from WebSocket? The short version is that WebSocket is a persistent client-to-server channel over TCP, perfect for chat messages and live events, while WebRTC carves a direct peer-to-peer path over UDP for low-latency audio and video. And here's the neat part, they're not rivals. Most real apps use WebSocket as the signaling layer to set up the WebRTC media stream. Now, peer-to-peer sounds magical until you try it with a group. In a pure mesh, every participant has to send their video stream to every other participant. So a 5-person call means each person uploads 4 separate streams. CPU spikes, bandwidth melts. That's why real apps introduce an SFU, a selective forwarding unit. Each peer uploads once to the server, and the server fans those streams out to everyone else. Same WebRTC under the hood, just one smart relay in the middle. Now, scaling aside, let's talk about safety, because here's the good news. WebRTC is encrypted by design. Every media stream rides over DTLS SRTP. Encryption is mandatory rather than opt-in. Browsers always ask before handing over your camera or mic. And the whole thing only works over HTTPS, but it's not a free pass. Peer-to-peer can leak your IP address to whoever you're calling. Your signaling server still needs hardening. Turn credentials must be guarded, and anything arriving on a data channel should be validated like any other untrusted input. With security covered, let's clear up a few myths that trip people up. First, WebRTC isn't entirely serverless. You still need signaling to introduce peers, plus stun and usually turn to get them connected. Second, it's not just for video. The data channel can shuttle any payload peer-to-peer, which is gold for games and file transfer. And third, peer-to-peer doesn't magically scale. Once you're past a handful of people, you'll want an SFU doing the heavy lifting. Speaking of SFUs, let's look at the tools you'll actually run into out there. On the browser side, Simple Peer and Peer.js are friendly wrappers that hide most of the WebRTC boilerplate. For servers, MediaSoup and Janus are the heavyweight open-source SFUs, while Coturn is the go-to stun and turn server almost everyone deploys. And if you'd rather not run any of this yourself, managed platforms like LiveKit and Daily handle the whole stack for you. Before we move on, let's lock in the big ideas. WebRTC is real-time, peer-to-peer media built right into the browser. A signaling server plays matchmaker. It introduces the peers, then quietly steps aside. Stun finds a direct path when it can, and turn relays the traffic when it can't. And remember, it's not just audio and video. Data channels let you send anything. Finally, group calls lean on an SFU because a pure mesh just doesn't scale. So with all that in mind, when should you actually reach for WebRTC? It really shines for live audio and video, screen sharing, low latency peer-to-peer data like multiplayer games, and anytime you want to cut bandwidth on your media server by letting peers talk directly. But if you just need plain text chat, a WebSocket is simpler. For basic request and response, stick with HTTP. For one-way server updates, server-sent events do the job. The rule of thumb, if the setup cost outweighs the benefit, it's probably not the right tool. If you want to keep going, the rest of the Networking Explained series pairs really well with this one. WebSockets, TCP/IP, TLS, and API gateways all touch the same world we've been exploring. And one important reminder, WebRTC encrypts your media by default, but your signaling and turn servers are still just servers exposed to the internet. If you're running them in production, harden them properly. The SSH Hardening Mastery course over at Dargslan.com is a solid place to start. Before we wrap up, I've got a quick question for you. Have you ever actually built something with WebRTC? Maybe a video chat app, a peer-to-peer game, a file transfer tool, or has the whole signaling, stun and turn dance kept you on the sidelines? Drop a comment and let me know. I genuinely want to hear what you've shipped or what's been holding you back. And that's WebRTC. From the costly problem of relaying every byte through a server to peers talking directly with the help of a little signaling magic. If this episode finally made it click, hit subscribe and stick around for the rest of the Networking Explained series. You'll find more deep dives over at dargslan.com. Thanks for watching. I'll see you in the next one.